Okay, good morning, ENET 140. This morning is the first of the recorded lectures for Fiore's Op Amps textbook, Chapter 4, and it's entitled Basic Op Amp Circuits. And here's where we kind of leverage, I guess, all of the theory of negative feedback that we went through in Chapter 3, and we kind of roll that all into a couple of big rules of how to deal with what we could consider idealized op amps that have negative feedback circuits hooked to them. And I think that's the most important thing to point out at this point, is that everything that we will be doing in Chapter 4 here, where we're using these idealized approximations, only applies if you have negative feedback operating on your op amp circuit. If not, then you're back to that open loop behavior, which is great for switching the comparator type circuits. So all of this will be with negative feedback, not in the open loop mode. So that out of the way, I'll just start going through my notes here. And again, I will be using my notes from Fiore's Chapter 4, just like I did in the recorded screen capture lectures for Chapter 3. So we will be looking at practical applications of negative feedback, and the main uses for these are going to be with small signal linear amplifiers. What is a small signal? Well, it's relative to the capabilities of the op amp. Generally speaking, we would look to be maybe an order of magnitude away from the supply voltage limits and well below the current output current limits of the op amp. So just like we were in our small signal BJT amplifiers back in the semiconductors course, we're probably in the millivolt, like 100 millivolts max region here, not volts, and definitely in the a few milliamps output, maybe up to 20 milliamps being the typical max output for a lot of general purpose op amps. Most important, we're going to be working in the mid-band frequency. So we don't have to be concerned with that 20 decibel per decade of frequency roll-off for lagging or leading behavior as we roll off of the midband. We're going to be working squarely in the middle of the midband, or we're going to be presuming that we are. And so these assumptions will hold for those conditions. So before you start using all these great formulas for gain that we're going to be deriving, make sure that these conditions apply in your circuit. Okay, so what are these idealized approximations? Well, the first one is that our input impedance into either the inverting or non-inverting terminal is infinite. So we can say our input current is zero. So if we have current heading into the op amp as a result of our input voltage signal, maybe dropping some voltage over a resistor, it either has to go to ground or it has to go around, so to speak, the op amp through the feedback network. We're going to assume that it's effectively an open. The next thing we'll assume is that the potential difference that we can assume at the inverting and non-inverting terminals is zero. So Vn inverting and Vn non-inverting will assume the same potentials. Now that's got to bring up a question like, wait a minute, that potential difference, whether it's a V diff in an open loop condition or a delta V error in a closed loop feedback condition, isn't that the difference that the op amp is operating on and is going to use to amplify? Well, yes, it is. And that's why we call this an idealized approximation. In reality, there is a tiny difference between the two. But we are assuming, again, in our ideal world, that the closed loop gain from the feedback network is effectively infinite, or excuse me, the loop gain is infinite, and so the V error can be zero. So we're multiplying zero by infinity, and so we get our output. We'll still be calculating gain using the feedback resistors, but this no potential difference between the input and the output is going to be a very powerful assumption that we make as we march through our circuit analysis. So at this point, I would not get overly worried about the circuitry that's accomplishing that and exactly how it affects any of our internalized op amp circuit models, and just go forward remembering these two, and then in later chapters, I believe in chapter 5, we will probably come back and address under what conditions we have to back off from that assumption. But these assumptions hold in the vast majority of cases in which we have small signals and we're in the midband. And so it's definitely worth running forward with them, as they will be useful for us. Okay. Upshot of these rules: most of the op-amp circuit behavior is defined by the feedback resistor network. So we effectively end up replacing the triangle of the op-amp with these two rules. No current goes in, and V-in inverting and V-in non-inverting are the same, reference to ground, and then everything else just simply becomes a DC or AC simple circuit network going through the feedback network. So we'll explore all the different ways that we can apply those rules, or not all the different ways because there's an infinite number of ways, but we'll explore some of the mainline applications. And these will fall into a couple of different categories. The two most important being the non-inverting voltage amplifier and the inverting voltage amplifier. For the most part, op-amp circuit networks are used to amplify voltage signals, although they can amplify current signals, and they can transfer a voltage signal to a current and vice versa. Remember those 4 different types of negative feedback networks we saw in Chapter 3, the series, parallel, 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 etc. That's how those are used. But really, voltage to voltage is the most common application, so we'll spend a lot of time on that and then look at the differences that we'll get as we go to current or current to voltage. Okay, so starting off with application number 1, the non-inverting voltage amplifier. So here we have our idealized op-amp with our non-inverting terminal and our inverting terminal. We have a voltage signal coming into the non-inverting terminal, hence non-inverting voltage amplifier. We have our output voltage. It's going to produce some current across a load, but we're mainly concerned with our Vout signal. And we have what's called R sub I, and that means inverting terminal resistor, and that's a convention that you'll see continuously through this chapter. And then RF, which means feedback resistor. So the combination of RI and RF forms our feedback network, and this is something that I think we saw in Chapter 3, where these two resistors are going to act like a voltage divider and define our beta, our feedback fraction. But rather than looking at a feedback fraction beta per se, we're going to use those idealized rules, and we're going to define the Vout divided by V-in ratio for our AC signal that we're going to try to be amplifying here. It's an amplifier. It's the whole point of this thing being here, in terms of VF and VI. Okay. So we're going to apply our ideal op-amp rules. We're going to start with that V error equals 0. So we're going to define the voltage at the non-inverting terminal as V sub A, just for ease of use, and the voltage at the inverting terminal, which could also be called V sub F because it's the voltage as a result of our feedback, but we'll call it V sub B just to make it easy. And we'll take a look at our resultant circuit diagram here and draw some current arrows. So if we start at V sub B and we're looking into the op-amp through the inverting terminal here, well, we can first say there's no current flowing because this has infinite input impedance here. So it's an open, so there's no current flowing through there. So if I want to look at whatever current may or may not be flowing from V out to ground, I can define it as I sub F, meaning I feedback, because it's flowing through the feedback network. I can define it as V out minus the voltage at ground, which is 0, divided by the resistance of the path to ground, which is, oh hey, this is just a series resistor path, RF plus RI. Well, that's pretty easy. And if I want to define the voltage at VA, well, I can use the fact that V error is 0 and VA equals B and say, well, my voltage up here is the same as my voltage down here, which is the voltage here. Now, if I wanted to express V sub B with reference to ground, I could just say, well, the voltage with reference to ground is going to be the current flowing through whatever resistance is between me and ground times that resistance. So in this case, since I sub f has to flow through R sub I to ground and no other currents flow through R sub I, V sub B is just R sub I times I sub f. So there we go. We now have a way of expressing the input voltage reference to ground and the output voltage reference to ground. So we can say V out equals divided by the series combination of R sub I and R sub f equals I sub f. We can define V sub B the same way. V sub A is going to be V sub B. So we can do a little algebra. V sub B is V out times V inverting divided by the series combo of the V inverting plus the R feedback. Since VB equals VA, VA equals VN. Do a little algebraic manipulation, divide Vn to the other side. We get an expression for gain, for voltage gain, and this is the gain ratio, not in decibel scale, of RF plus RI over RI, and we can distribute the 1 over RI and get 1 plus RF over RI. And this should look a little familiar. I think we saw this in chapter 3, but if not, we're seeing it here. Notice that the current expression, the current feedback current canceled out, and so we have a unitless voltage ratio, resistance ratio. So notice any property of the op amp is not present. Didn't start with it, don't end up with it in the gain ratio. We don't have any betas or our open loop gains like we did in chapter 3. The gain is only dependent on the ratio of the input and the feedback resistor, actually the inverse. Now a note that the textbook author that Fiore makes is that typically for practice R sub I and R sub f will be in the 10 to 100 kilo ohm range, and I'm assuming that that is for just to limit currents going in and out of the op amp. Again, even though it's infinite input impedance, there is a little bit of current that flows, and especially we tend to have current limitations on the output. Again, you'll probably see 20 milliamps quite a bit in your spec sheets. And so by using larger size resistors, we just make sure we don't have some runaway condition where we're drawing too much current out of the op amp and blow the top off of it. So we can work through an example, and we can go either one of two ways. We can look at analysis and get an idea of the gain for a circuit that someone else has built, or we can take a need, like, okay, I need a circuit with this much gain or this much input impedance, and then decide what resistor or feedback network we need to achieve that. So this first question is an analysis. So you've got a non-inverting voltage amplifier because you have a voltage coming in, and then you've got your feedback current coming out, and somebody wants to measure voltage here. And you've got a big load resistor which will prevent a lot of current flowing to ground. So somebody wants to know the input impedance and the gain. Well, the first one's really easy because we don't have any other paths to ground from our input signal. The only path to ground is through the op amp, which we've already defined as having infinite input impedance. So we know Zn is infinity. So now all we have to do is get the gain. You know, we can go through our KVL loops again and ratio. We can just walk ourselves through and say, well, you know, this voltage is the same as this voltage because our two input terminals have to be the same. And then this voltage is going to be whatever current flows through this resistor times 1 kilo ohm. That's the same current that flows through this path from the output. And then the V out is going to be that current times these two and ratio them. So we could do that in our head if we wanted to, which will of course give us the same formula we just derived, but we can just drop it in and say here the gain is going to be 1 kilo ohm plus 10 kilo ohms over 1 kilo ohm, so it's 11. So we have a gain of 11, and that's a fairly popular number that you'll see in negative feedback loops. We saw that quite a bit in chapter 3. Okay, so here's a design problem. These are all examples out of Fiore's book. You can step through them with Mr. Fiore after you listen to this. So somebody needs an amplifier with a decibel scale gain of 26 decibels. And they needed an input impedance of 47 kiloohms. Design a circuit around a general purpose op amp that'll do that. So step one, wait a minute, how do we get 47 kiloohms when an op amp has infinite input impedance? Well, you go around it, basically. So we'll knock this first one out really easily by putting a 47 kiloohm resistor on a direct path to ground at Vin. No current's going to go into the op amp, so if we put a resistor bridging the input signal to ground, that will by definition give us a 47 kiloohm path to ground. Why they needed that, I don't know, but it was in the spec. Okay, so next all we have to do is get gain. So remember that our 1 plus RF over RI that we derived specifically in terms of a voltage ratio. So let's get that log scale gain into a voltage ratio scale. So we just apply our definition of decibel gain. Always reference to power, so we got our 20 multiplier. So we can say 26 decibels is equal to 20 times log base 10 of our voltage ratio gain. And so we just divide by 20 on both sides, take the inverse base 10 log, and we get a voltage ratio gain of 20. And so that's going to be equal to 1 plus RF over RI. So we end up finding out that we need an R feedback over RI of 19. So there's any kind of number of resistors that would work. If we chose a couple that were on the high side, we could, for instance, choose 10 kiloohms for RI and 190 kiloohms for RF. Or we could any kind of series combo to get that 190, because the 190 kiloohms is not a standard size. We could go on the low side or the high side, but we would have to retain this ratio to retain the gain that we needed. So here's a schematic of what we would end up with. Here's our 47 kiloohms bridging our input signal to ground. So we have infinite impedance, input impedance here. So our impedance to ground would go on this path, and we've defined what it is according to the spec, and then put in our feedback network to satisfy our gain. What if we need a gain of 1? Well, let's see what our gain formula that we just derived would tell us. So our voltage ratio gain is 1 plus RF over RI. Well, RI can be anything, but for our voltage ratio gain to be 1, RF has to be 0. Well, that's easy to do. We'll just short across it with a wire. So this schematic shows us our absolute simplest voltage follower, where we've got we've effectively got infinity, infinity, sorry, for R sub I. We've got an open. We haven't connected the op amp to ground at all, so it's floating unless we have a ground on the input, which may or may not be advisable. But we definitely have an RF of 0. So you can see we have no feedback resistor, we just have a 0 resistance wire. So this defines a classic voltage follower. In practice, we'd probably have some kind of large resistor going to ground, just to reference the whole circuit to ground. But what makes it a voltage follower and gives it the unity gain is the fact that we've literally shorted the output to the inverting terminal, so RF is 0. So that's pretty easy if we need to have the control of an op amp, but for whatever reason we don't want to be giving any voltage gain at a given stage. Just leave RF out and short it. Okay, so speaking of different amounts of gain, what if we need to get more gain than is available from a single op amp, and how would we know that we're at that limit? The best way, and we may or may not have touched on this already in chapter 3, but if your calculated output current dropped over your load to ground exceeds your supply voltage, you will get the supply voltage. You'll be back to being just a comparator. So say you have a supply voltage of effectively the 13.5 and you need 25 volts output. Well, you're going to have to gang them up and use a couple of op amps to do that, each one giving you bigger input. This is called cascading or multi-stage op amps. Regardless, each time you will still need to be aware of what the supply voltages are. Be aware of exactly where your power, where your energy is coming from for any given stage. Just because you have a gain doesn't mean you'll get the output. But generally, ganging up a couple or more, cascading, is a great way of drawing in some energy from your supply at each stage so you can end up having a bigger output. Well, we can walk through the math for this actually, and we can look at a given input signal and see how it's being amplified to get to this output point, and then take that output signal and feed it in as an input and go through the same calculations all over again with a new input and the feedback resistors forming our gain network, and see what we get. So we could start by defining the gains for each one. So we can use the formula we derived already to get the voltage ratio gain of amplifier number 1 will be 1 plus 14 over 2. So that's 8. And for amplifier number 2, we'll have 1 plus 18 over 2. Remember, RF over RI, the equation we just derived, so we have a gain of 10. And we can get a voltage ratio, or excuse me, a voltage-based input signal. It's we've got a dBV negative 30 coming in. So that's a voltage signal. That's not a ratio. That's not a gain ratio. That's actually just a signal in volts coming in. So this is where we're using the reference voltage of 1 volt to define it. So let's turn that 30 dBV into actual volts. And we'll use, again, our conversion formula from decibel to voltage ratio. And this time it's a voltage ratio to our 1 volt reference. So we do that, we find out we have a V in of 316 millivolts. And the first thing we might want to do is say, is that in the range of a small signal that we would for which we'd want to be using these idealized approximations? Yeah, it might be a bit on the high side, but it's definitely not like 10 volts or something coming in. So we're good there. So we'll march ahead with our approximations. One thing we can do is remember that when we have a multi-stage set of amplifiers, we can typically multiply the gains. So we can just take the gain from op amp 1 from amplifier 1 times the gain from amplifier 2 expressed as voltage ratios. And so we get a total gain of 80. And if we wanted to go back and express that gain in decibels, we could apply the 20 log base 10 and get that expressed as a decibel gain. We can walk through the math as well and do it for each stage. Let's see, which I don't have here in my notes, but that's definitely a good exercise. You could put 316 millivolts in here, multiply by your gain, and get a larger signal coming in here, multiply by your gain and get the V out. You can take your total gain of 80, apply it back to the input voltage signal, and look, you're getting 2.53 volts on the output. And then you can convert that back to a decibel equivalent if you wanted to. And this is big enough that you would want to be careful that you can definitely supply it with your supply voltage. You'd be giving that 13.5 volts typically if you had a 15 volt supply, so we're not exceeding that. You would want to be careful that you did not exceed your current output if you had a very small resistor going to ground with that. But otherwise, that would be your V out, 2.5 volts for 316 millivolts in. And if you enjoy working in decibels, you can go that extra mile and say let's express our voltage gains for each stage in decibels. So you could take your 8 voltage ratio gain for amplifier 1 and turn it into a decibel expression of 18, and then your 10 voltage ratio gain in amplifier 2, turn it into a decibel gain of 20, and then all you do is add. You add your voltage input signal in dBV, which is -30, to your gain for amplifier 1, which is 18, plus your gain amplifier 2. So remember, that's that property of natural logs. You can multiply and take the log, and then you get the sum of the logs. And so that gives you -30 plus 38, which is 8 dBV, which is the same as if we converted from our voltage ratio. So that provides you a little check. So that's 2 or 3 different ways to do it. So takeaways: gains multiply when you have cascading amplifiers. You are drawing power in from your supply rail at both stages, so you can get a bigger power out in the final output. You multiply the gains as voltage ratios, you add the gains as decibels, and be sure to convert inputs and outputs to the desired decibel or voltage reference. Okay, we are going to stop here and pick up with another lecture for the inverting voltage amplifier. We'll probably end up with at least 3, maybe 4 individual lectures here for chapter 4. It's a fairly big chapter, but the derivation for your gain equation, where we use the feedback network, you'll probably notice that we were whether formally or informally using Kirchhoff's voltage law and Kirchhoff's current law to derive our gain equation. And we can either use that equation or just look at the circuit sometimes and do a little KVL in our heads and get the gain, or do both and be really sure. We're going to do that again and again with more and more complex circuits, always applying those 2 rules of idealized negative feedback equipped op amps, infinite input impedance into the inverting and non-inverting terminals, equal potential versus ground at the inverting and non-inverting terminals. And we'll put that together with KVL and KCL and analyze at least 3 or 4 interesting circuits that have a lot of uses.